Hello everyone, my name is Vibin Abram, and in today's video we are going to talk about electric dipole in uniform electric field. So let's get started. Okay, so in the previous videos we have talked about force, we have talked about electric field, we have talked about electric dipole, right? So let's quickly recap what electric dipole was, right? So what was our electric dipole? Electric dipole was an assembly of two equal and opposite charges, right? For example, I have a charge plus q, then the other charge will be minus q. If it is separated by some distance, let me call the distance to be r, then this assembly of equal and opposite charges separated by some distance is what we call as your electric dipole, right? I hope that is understandable. Then there was electric dipole moment, right? So what was electric dipole moment? Electric dipole moment was given as P, right? And it was defined as magnitude of one of the charge, that is your plus q. If I talk about this case, then there is plus q, magnitude of one of the charge, right, multiplied by the displacement vector. So in this case displacement vector is r, right? So q times of r is your dipole moment, right? And dipole moment, obviously it's a vector quantity, so definitely it must be having a direction. So direction is always from minus q to plus q, right? So these were some information which we already did in our previous videos, right? So before I start today's topic, we need to go through some notes which are going to be useful for today's video. So without wasting time, let's go to those notes. Note number 1, right? The note number 1 says, let me read it out: if charge plus q is placed at a point where electric field is E, okay, then charge particle is going to experience a force which is given as F equals to QE, and it will be in the direction of the electric field. Okay, so what does this note says? The note says that if plus Q charge is placed at a point where electric, okay, well, let me first draw electric field, right? So let's say this is my electric field, let me call it E, right? Okay, now according to the note, if plus q charge is placed at a point where electric field is E, okay, so I have to place plus q charge. Okay, this is my plus q charge, I'm going to place it, let's say some point here. So my plus q charge is where electric field is E, right? Okay, then charge particle is going to experience a force which is given as F equals to QE, right? So according to this note, this charge particle is going to experience a force which is actually F is equals to QE, and it will be in the direction of the electric field, right? So this charge particle is going to experience a force, right? This charge particle is going to experience a force which will be in the direction of your electric field, and it is given as Q times the electric field. This is the force that this charge particle plus charge particle is going to experience, right? I hope the first note is understandable, right? Okay, let's go to the second note. The second note says, if minus q charge is placed at a point where electric field is E, it is again going to experience a force F equals to QE, great, in the direction opposite to the electric field. The only difference is this time the direction will be opposite, right? So let's draw that too, right? Okay, so the first thing, the electric field, this is my electric field E, right? This time I have to bring a minus q charge instead of positive q, right? So I'll bring a minus q charge, right? And I'm going to place this minus q charge somewhere here on the electric field, right? So according to our note, it is going to experience a force which is again given by F is equals to QE in the direction opposite to of electric field, right? So this time the direction will be different, right? So electric field is in that, if electric field is in this direction, then the direction of force will be in this direction, right? So let me just draw it. I hope you guys can see the arrow, right? The green arrow is giving me the direction of force which is given as Q times of E, right? Where Q is the charge, Q is the magnitude of charge, E is the electric field, right? See, the magnitude is minus Q, but I'm actually taking it Q because minus Q is actually telling you a direction. That is something which you have to understand, right? Clear? Okay, great. Let's move forward, right? Let's go to our main topic. The main topic was that electric dipole in uniform electric field. That means you have placed your electric dipole in a uniform electric field, right? Now what is going to happen? Let me just first draw the uniform electric field, right? So let's move to the topic. Okay, so this is electric dipole in uniform electric field. Okay, right. So first I have to make the electric field, right? Okay, let's make the electric field. This is my first. Now remember, this is uniform electric field, right? That means everywhere the effect of electric field is same. This is something which you have to understand. That's why I have, I'm drawing it with parallel lines, and let's assume that gap between these parallel lines are same, right? Let me call this electric field to be E, right? Great. Now I have my electric field. I have to draw my dipole now. Okay, so we all know what a dipole is, right? I'm sure everybody knows what a dipole is. Dipole is an assembly of, yes, minus q, and let me say this is my plus q charge, right? So it is an assembly of minus q plus q charge, and let's say they are separated by a distance of 2a. 2a is the different distance between my minus q and plus q charge. So I have a dipole inside my uniform electric field, right? So two things I'm going to find out here, right? Two things I'm going to find out. Number one is the net force that is acting on the dipole. Net force acting on the dipole, right? What will be the net force that is acting on this dipole, which is like kept in this uniform electric field? That is the first thing that I'm going to find out. Second is obviously torque. Okay, we'll talk about torque, right? Torque experienced by it. We will talk about from where this torque is coming from and how much torque it is going to experience. We will talk about, right? So let's first talk about the net force acting on the dipole, right? The net force, that is the total force that is acting on this dipole, right? Now how am I going to find that out? Great. So it's very simple. We have our notes to refer, right? So first note was, if a positive charge is kept inside a uniform electric field, or it is kept inside an electric field of E, right, then it's going to experience a force in the direction of the electric field. And if you have negative charge, it's going to experience a force which will be opposite to the direction of the electric field. Yes or no? Great. Remember that part. So basically you guys can see there is this positive charge. Yes. So obviously it's kept inside a uniform electric field. It is going to experience a force which will be in the direction of electric field. Yes, right? And it will be given as F. Let me call this force to be F1. F1 will be equals to, magnitude will be Q times of the electric field. Yes or no, right? Here I have a negative charge which is inside the electric field E, right? And obviously it is going to experience a force which will be in the direction opposite to the field, electric field, and the magnitude will be F2 is equals to Q times of E. Yes or no? I hope that is understandable. So I can just write it down. For example, I can write the force experienced by plus Q charge inside electric field E. Electric field E. Yes, right? And that will be given as, yes, that will be given as F1. Let me call it F1 vector, right? F1 vector is equals to, right, this will be Q times of electric field, and the direction will be along the electric field. Yes or no? This is my equation number 1. I hope that is understandable, right? Okay, the force experienced by minus q charge inside electric field E, right? Again, you guys can see the force is same, but the only difference is this time is the direction, right? So I can write it here. Let me call this that force to be F2 vector, and that is Q times of E, but opposite to the electric field, right? I hope that is understandable. This is equation number 2, right? I hope that is clear, right? So I'm supposed to find out the net force that is acting on this dipole, right? And I can say, and very nicely I can see it over here also, right? So because of positive charge the force is in this direction, because of negative charge force is in that direction, right? So I can draw it even here also. I can see because of positive charge force is in this direction, and because of negative charge force is in that direction. There is an angle of 180 degree between these two forces, and I know both have the same magnitude, QE and QE. Yes or no? So if I do the net force, I can write it net force on the dipole. Net force on the dipole will be simply given as, yes, F net, let me call it F net vector, which will be simply equals to F1 vector plus F2 vector, right? Or very simply, as the direction is 180 degree, I can simply write Fn to be F1 minus F2 vector. I hope you can vectorially understand it, because obviously what is going to happen here, you will apply the formula, right? That is F1 vector square plus F2 vector square plus 2 times of F1 vector F2 vector and cos of 180, right? Cos of 180, and you know cos of 180 is -1, and this will become F1 minus F2 whole square, and the bracket by cancel, and we are left with this result, right? And I know Fn will be simply, this is Q times of E minus Q times of E, and finally the answer is Fn vector will be simply equal to 0, right? They will cancel each other out because they are equal and opposite. I hope that is obviously, this is you guys can see this is my vector, like this is my vector which is like inside my electric field, right? So here there is this force, here there is this force, right? Both are equal and opposite, so the net force that is acting on this dipole is actually 0, right? As you guys can see in this diagram. I hope that is understandable. Yes, great. So if that is understandable, that brings to my next part of the question, that is the torque, right? So from where the torque is coming, right? So we have studied now 11th standard, whenever there is a couple of forces that is acting equal and opposite on the edges of this kind of, let's say, pen, right? So let's say I have applied a force like this, right? You guys can see the moment I applied this force, there is some force which is like, you know, giving it uprising effect, right? So there is a couple. The moment I bring this down, this will also come up, right? So you guys can see this effect, right? This effect is what you call as your torque, right? Torque on this particular pen, right? So very nicely you guys can see, for torque to happen there must be couple of forces, right? So in this example you guys can see there are a couple of forces, right? So tell me, the net force is 0, but because of these torque, will there be a rotation? Yes or no? You guys can see there's a torque like this, so because of that torque, will there be a rotation? Will the dipole move? You guys can see this is the dipole. One force is this direction, one force is this direction. So because of these couple of forces, the dipole is supposed to move. There will be a torque on the dipole. Yes or no? Right? Because of that torque, the dipole is supposed to move. I hope you guys can visualize that. Yes, great, right? So I'm supposed to find out the value of torque, right? So before I find out, I need to do some, you know, some mathematics over here, right? I need to do some geometry. So I can see over here, this is, I can just say this is my electric field, right? So the angle between the dipole and the electric field, let me call it some theta angle, is there, right? Okay, so if that angle is theta, so I can very nicely write it here. I can have two components. This is 2a cos theta, and very nicely this distance is 2a sin theta? Yes or no, right? And okay, so let me go to down. I have to find out the torque, right? This is the next part, that is the net torque. Net torque acting on dipole. So I know the value of the formula for torque. The formula for torque is simply given as magnitude of one of the forces. I hope you guys remember this formula. One of the forces multiplied by the perpendicular distance, right? The perpendicular distance between them, right? This is how we are supposed to find out the torque, right? So you guys can see over here, you guys can see in the diagram. So the one of the forces is actually QE, that is my force. QE is one of the force, but the perpendicular distance between them, you guys can see which distance is perpendicular, right? So my force is like this, my forces are like this. So tell me, is this distance the perpendicular distance? Yes or no, right? So you guys can see this is my force, this is my force. So tell me, is this distance is the perpendicular distance between them? Yes or no, right? So you guys can see 2a sine theta is the perpendicular distance between them. I hope that is understandable. Yes, right? I hope you guys can see that, right? Great, right? Okay, so let's complete this, right? So this is torque, magnitude of one of the forces, that is q times of E multiplied by 2a sine theta, the perpendicular distance between them. Yes or no, right? Okay, now important thing, this q times of 2a, right, that is magnitude of one of the charge multiplied by displacement. This is your dipole moment, right? I hope everybody remembers it, right? We have discussed this in the start of the video, right? So this will be your p times of E sine of theta, right? And I can write it in the vector form. How I know? For example, if I write a cross b, then I can write my a cross b as ab sine theta, right? Very nicely I can write this torque as p cross E. Yes or no, right? Nicely, pe sine theta, it's fine, the same thing, right? So as I can write a cross b as ab sine theta, very nicely p cross E can be written as pe sine theta. Yes or no? I hope that is understandable. Yes, right? So the net torque will be given as p cross E or pe sine theta. It depends upon the theta, the angle between your p vector. Okay, let's go back to the diagram so that you guys can see that, right? So it depends upon, you guys can see from minus q to plus q is your dipole moment, right? And this is my electric field, right? Let me use different pen. This is my dipole moment, minus q to plus q, and this is my electric field. The angle between them is theta. So the torque depends upon theta. Torque depends upon the angle made by the dipole moment and the electric field, the angle made by them, right? It depends upon that. I hope that is understandable, right? Okay, so based upon this, we will talk about two different cases, right? So let me just discuss those cases. Case number one. Now in this case, you guys can see, let's say I have this uniform electric fields. I have these uniform electric fields. Okay, they don't seem uniform, but okay, let me make them uniform. Okay, I have these uniform electric field. Yes, great, right? And inside this, let me say I have my dipole. This is my minus q charge, this is my plus q charge. So obviously I have this dipole moment in this direction. I hope you guys can see that I have dipole moment in this direction, right? So the first thing that I can understand from here is, number one, the theta, the angle between your the angle between your electric dipole moment and your electric field is actually 0. As you guys can see, electric field is in this direction and this direction is your electric dipole moment, right? I hope the angle theta is something which you guys can understand now, right? Okay, the second thing is the net force. Okay, you guys can see, we guys can do that, the net force, right? So because of positive charge, it is going to experience a force which will be in that direction along the electric field. Because of negative charge, it is going to experience a force which will be in that direction, right? This will be F2, right? So I guess you guys can see forces are equal and opposite, right? And direction is this. So very nicely I can write force, net force is actually 0, right? Great. The third thing is your torque. What about the torque? What will be the value of torque, right? So I know the value of torque is given as P E sine theta, right? And I know the value of theta is 0 and sine 0 is 0. So can I write value of torque to be 0? Value of torque to be 0 because the angle between them is 0, right? So torque is 0. There is no torque acting on it. If there is no torque acting on it, it is in stable equilibrium. That means it is not rotating. That is something which I have to understand, right? So I can write here, this dipole is known as, or known to, this dipole is known to be stable dipole, or dipole which is in equilibrium, right? Or I should say stable equilibrium, dipole which is in stable equilibrium. You can say it like this also, dipole which is in stable equilibrium, right? It is in stable equilibrium. For example, if you tilt your dipole, this time this is the stable equilibrium dipole. If you tilt it, it will start oscillating and it will come back after oscillating to its original position, right? So you guys write also, if we tilt this dipole, it will start oscillating, and after some time it will come back to its original position. Alright, I hope that is understandable, right? Great. Let's discuss the second case. The second case is, for example, I have uniform electric field. Yes, I have uniform electric field. Yes, so I have uniform electric field. Great. Now let's draw the dipole, right? This is my positive q charge, this is my negative q charge. Yes, so the dipole is from minus to, okay, the dipole is from minus to plus q, right? So this is my dipole. You guys can see that dipole is from here to here, right? You guys can see that, right? Okay, so okay, this is my electric field, right? So very nicely, three things. That is, first thing is theta. So theta, obviously you guys can see electric field is in this direction, dipole is in this direction, so angle is 180 degree. So theta is 180 degree. This is something which I hope everybody can see. Yes, great. Okay, next part is the force. What will be the net force on this dipole, right? So let's see. This is my negative charge. Because of negative charge, the force will be in this direction. You guys can see. Let me call this force to be F1, right? And this is my positive charge. Positive charge, the force will be in this direction, which will be along the direction of your electric field. So you guys can see both the forces are equal but opposite. One is in this direction, another one is this direction, right? So obviously they will cancel each other out, right? In this case also, the forces will cancel each other out. I hope, okay, there is no degree there, right? The forces will cancel each other out. Net force on this dipole is still 0. I hope that is understandable, right? Great. The third case is your torque. What will be the torque that is going to happen, right? So obviously torque is given as P times E sine of theta, right? And the value of theta is 180 degree, right? And we know sine 180 is actually 0, right? Sine 180 is 0. So again, the torque that is acting on it is actually equal to 0. So there is no torque that is acting on it, right? Okay, now if all the three things are understandable, now the question comes, what will happen if I disturb this, if I disturb this dipole, right? Now if I disturb this dipole, what is going to happen? It is going to start rotating like this. It is going to start rotating like a fan. Why it is going to do that? Because all the forces are in this direction. For example, you guys can see the forces are in this direction, right? So the moment I disturb it, the forces will be like this, and because of that it will provide a torque, and because of that the whole system starts rotating like a fan. You guys can assume that it is going to rotate it like a fan, right? I hope that's understandable, right? So very nicely, so this type of dipole is what you call as your unstable. This dipole is an unstable equilibrium, right? You guys can say that this dipole is in unstable equilibrium state, right? Next one, if we tilt and leave the dipole it will start rotating. Right? I hope that is understandable, right? The first equilibrium case was the case of stable equilibrium. This is unstable equilibrium. In the first case, if you tilt it, it will start oscillating and come back to its original position. And in the second one, if you disturb it, it will start rotating because of the torque, right? I hope that is understandable, right? If you have any doubt, you can comment it down in the comment section, and I hope all of you are doing good. Stay home, stay safe.